Welcome! In this session, we'll explore an intriguing problem titled Number 2092, Find All People with Secret. This problem challenges us to think critically about simulating interactions and tracking information spread. Let's dive in and uncover efficient ways to solve it. In this problem, we are tasked with identifying all the people who eventually know a secret after a series of meetings. Initially, only person 0 knows the secret, but they can share it with others during these meetings. We are provided with an integer n, which represents the total number of people, labeled from 0 to n1. Additionally, there is a 2D array called meetings, where each entry, x_i, y_i, time_i, specifies that person x_i and person y_i met at the time_i. During a meeting, if one of these individuals already knows the secret, they can pass it to the other person. Notably, person 0 can share the secret with the first person immediately at time 0. The goal is to determine all people who know the secret after all the scheduled meetings are completed. The output should be a list of these people, and the order of this list does not matter. To understand this problem better, let's look at an example. Suppose n is 6, the meetings array contains 1, 2, 5, 2, 3, 8, 1, 5, 10, and the first person is 1. The output for this input is 0, 1, 2, 3. Here's what happens: person 0 starts as the only one with the secret, and at time 0, they share it with person 1. Then, as the meetings progress, the secret is passed along to others. The problem requires us to carefully track how the secret spreads based on the times and connections between individuals. In this example, the sequence of events is as follows. At time 0, person 0 shares the secret with person 1. Then, at time 5, person 1 meets person 2, and the secret is shared again. At time 8, person 2 meets person 3 and passes the secret to them. Finally, at time 10, person 1 meets person 5, but since person 5 is not connected to anyone else with the secret, they do not end up learning it. By the end, the people who know the secret are 0, 1, 2, 3. Now let's examine another example with n equals 4, meetings equals 3, 1, 3, 1, 2, 2, 0, 3, 1, and first person equals 3. The output here is 0, 3, 1. Initially, person 0 knows the secret, and at time 0, they share it with person 3. At time 1, person 0 meets person 3 again, but since both already know the secret, nothing changes. At time 2, person 3 meets person 1, and the secret is passed to person 1. However, at time 3, when person 1 meets person 2, the secret does not spread further because there is no connection that allows propagation beyond this point. Thus, the people who know the secret in the end are 0, 3, 1. There are several edge cases to consider when solving this problem. For instance, if no meetings take place, only person 0 and the first person will know the secret. If the total number of people is small, such as n equals 2, the solution must still correctly track the propagation of the secret. Another scenario is when the meetings array contains only one meeting. In this case, whether the secret spreads depends entirely on the participants. Additionally, when multiple meetings occur simultaneously, it's important to ensure that all these meetings are processed correctly to avoid any inconsistencies in the propagation logic. To begin exploring this problem, let's first consider the brute force approach. The intuition here is to simulate all possible meetings and track how the secret spreads from one person to another. For every meeting, we check if either participant already knows the secret and, if so, propagate it to the other participant. This process is repeated for all meetings, which are sorted by their time value. Sorting the meetings chronologically helps us maintain a clear timeline of when each person learns the secret. Now, to optimize this approach, we can use a union-find data structure, also known as disjoint set union or DSU. This allows us to group people into connected components, essentially clusters of individuals who share the secret at the same time. However, the brute force approach has significant drawbacks. Its time complexity is high because it involves redundant checks. If there are m meetings and n people, processing each meeting for all individuals results in a worst-case complexity of m*n. Additionally, this approach does not fully utilize efficient data structures, leading to unnecessary computations and poor scalability. Now, let's look at an optimized approach that addresses the inefficiencies of brute force. First, we still sort the meetings by time, which allows us to process interactions in chronological order. This ensures that earlier interactions are handled first, maintaining the integrity of the timeline. Then, we use a union-find structure to group people into connected components. If one person in a group knows the secret, the entire group learns it. A key improvement here is using a temporary DSU for time-bounded propagation. This means that instead of permanently merging connections, we temporarily track groups for each unique timestamp. Once all meetings for a specific time are processed, we check which groups contain person 0, the source of the secret, and propagate the secret to everyone in those groups. The algorithm works as follows. First, sort the meetings by time. Then, for each unique time, process all meetings that occurred at that timestamp. Using a temporary DSU, merge the participants of each meeting into the same group. After processing, verify which groups include person 0 and mark all individuals in those groups as knowing the secret. This process is repeated for each subsequent timestamp, ensuring that the secret is only propagated when valid. In terms of complexity, the optimized approach is highly efficient. The time complexity is O, m asterisk alpha, n, where m is the number of meetings, n is the number of people, and alpha is the inverse Ackermann function, which is extremely small and grows very slowly. This makes the DSU operations nearly constant time. The space complexity is O, n, as we only need space to store the DSU structure for the people involved. A key observation is that by isolating interactions at each timestamp, secrets are only propagated within valid time windows. This ensures the integrity of the solution. Additionally, DSU efficiently manages group merging in connected component queries, minimizing redundant computations. Ultimately, we chose the optimized approach because it strikes a balance between clarity and efficiency. Unlike brute force, this method scales well for large inputs and avoids unnecessary checks by leveraging DSU to process connections intelligently. Finally, let's compare the trade-offs between the brute force and optimized approaches. The brute force method is simpler to implement and may be appropriate for small inputs, but it becomes computationally expensive as the input size grows. On the other hand, the optimized approach is slightly more complex but significantly more efficient. By using a combination of sorting, DSU, and temporary state tracking, it eliminates redundant computations and ensures scalability. The chosen strategy guarantees correctness by processing meetings in chronological order and only propagating the secret within valid time windows. This makes it both robust and well-suited for larger datasets, providing a practical and efficient solution to the problem. To solve this problem, we start by understanding the propagation of a secret through a series of meetings. The goal is to determine which people eventually know the secret after simulating its spread. The secret starts with one person, and during a meeting, it can spread to another person if one of them already knows it. Meetings are processed in chronological order to maintain the correct sequence of events. We begin by parsing the input to extract the meetings, where each meeting is represented as a tuple of time and the two participants involved. We also initialize an array, knows_secret, to track who knows the secret, starting with the original holder, usually person 0. Then, we sort the meetings by time to ensure proper simulation. Next, the secret propagation is simulated by iterating through the sorted meetings. For each meeting, we check if either participant already knows the secret, and if so, we update the array to reflect that both participants now know it. To make the propagation process more efficient, we use a union-find data structure, also known as a disjoint set. This helps in tracking groups of people who can share the secret. The union-find operations include the union function, which links two participants if they meet, and the find function, which checks if a person belongs to the same group as the original secret holder. After processing all meetings, we use the union-find structure to propagate the secret to everyone in the connected component containing the secret holder. This ensures that we only process relevant groups and avoid unnecessary computations. Edge cases also need to be carefully handled. For example, if there are no meetings, only the initial secret holder will know the secret. If there are disjoint groups that never connect to the secret holder, those groups remain unaware. Additionally, when multiple meetings occur at the same time, they are processed independently but in the correct order to maintain consistency. Finally, we determine the result by iterating through the knows_secret array or using the union-find structure to identify all individuals who know the secret. The key to this algorithm lies in a few important insights. First, sorting the meetings by time is essential to ensure they are processed in chronological order. This guarantees that the simulation reflects the actual sequence of events. Second, the use of union find greatly optimizes the process. Instead of repeatedly checking and updating the knows_secret array, union find allows us to efficiently track connected groups of people, reducing the time complexity significantly. This is especially important in scenarios with a large number of meetings. The propagation mechanism is another critical aspect. The secret spreads only within connected components of people, which minimizes unnecessary checks and ensures the algorithm remains efficient. Two main data structures are used: an array, knows_secret, which directly tracks the status of each person, and union find, which is better suited for handling larger and more complex cases by efficiently managing group connections. Analyzing the algorithm's complexity gives us a clearer picture of its efficiency. The time complexity is dominated by two factors: sorting the meetings, which takes O(m) log m, and the union find operations, which are nearly O(m) for m meetings due to their amortized efficiency. Together, this gives a total complexity of O(m) log m. The space complexity is O(n), where n is the number of people, as the union find structure requires storage for each person. Let's understand this with an example. Suppose we have meetings 1, 0, 1, 2, 1, 2, 3, 3, 4, and the initial secret holder is person 0. First, we sort the meetings by time, which results in the same order. At time 1, persons 0 and 1 meet, so both know the secret. At time 2, persons 1 and 2 meet, spreading the secret to person 2. At time 3, persons 3 and 4 meet, but since they are in a disjoint group, the secret doesn't spread to them. The output is 0, 1, 2, representing the people who know the secret. This algorithm is highly efficient in handling the spread of the secret across meetings. By leveraging the power of the union find data structure, it avoids redundant computations and ensures scalability even with a large number of meetings or people. The combination of chronological processing, efficient group tracking, and careful handling of edge cases makes this approach robust and well suited for the problem at hand. Here, we begin by importing the necessary modules, defaultIct and deque, which will help us manage the data structures for this problem. The solution is defined inside a solution class with a method findAllPeople, taking three parameters: n, the total number of people, meetings, a list of tuples representing when two people meet, and first person, the person initially sharing the secret with person 0. The first step is constructing an adjacency list, meetings_by_time, which groups all the meetings by their timestamps. This allows us to process meetings in chronological order later. Each meeting is added to the corresponding timestamp in the dictionary. Next, we initialize a set called knows_secret containing person 0 and the first person, as these two individuals start knowing the secret. Then, using a for loop, we iterate over the meetings sorted by their timestamps. For each time, we create a graph represented as a defaultIct of lists to store connections between individuals who meet at that specific time. Simultaneously, we gather all unique people involved in these meetings into a people set. To construct the graph, we loop through the meetings at the current time, adding bidirectional edges between the two individuals who meet. Finally, we initialize a queue containing all people who already know the secret and are part of this people set. A visited set is also initialized to track which nodes in the graph have been processed. Using the queue, we perform a breadth-first search to identify all individuals connected to the people who already know the secret. At each step, we dequeue a person and examine their neighbors in the graph. If a neighbor hasn't been visited yet, we mark it as visited and add it to the queue for further exploration. This process ensures that we traverse all connected components of people who can pass the secret at the current timestamp. Once the BFS completes, we update the knows_secret set to include all individuals visited during this step who are part of the current people set. This ensures that only those directly connected to someone who knows the secret at this time are added to the group of people with the secret. After processing all timestamps, the method returns the list of individuals in the knows_secret set as the final result, representing all the people who know the secret by the end of all the meetings. Here, we begin by grouping the meetings by their scheduled time using a tree map, which ensures that the keys are sorted in ascending order. Each key in the map represents a specific meeting time, and the corresponding value is a list of pairs of people who are meeting at that time. This structure allows us to process the meetings in chronological order. Next, we initialize a set called NoSecret, which will keep track of all the people who know the secret. By default, person 0 knows the secret, and we also add first person to this set since they are initially informed. Following this setup, we iterate through the meetings grouped by time. For each time slot, we construct a graph where the nodes represent people and the edges represent the meetings between them. Alongside this, we maintain a set of all the people involved in the current time slot to ensure accurate processing. Once the graph for the current time slot is built, we move on to identifying connected components of people who may learn the secret. To do this, we initialize a queue for a breadth-first search and a visited set to track which people we've already processed. For any person involved in the current time slot who already knows the secret, we add them to the queue and mark them as visited. This forms the starting point of our BFS. As we process the queue, we explore each person's neighbors in the graph. If a neighbor has not been visited yet, we add them to the queue and mark them as visited. This ensures that all connected individuals in the graph are explored. After fully traversing the graph, we update the NoSecret set by adding all the people from the visited set who are part of the current time slot. This way, the secret is propagated only among those who are directly connected during that specific meeting time. Finally, after processing all the meetings in chronological order, we return the result as a list containing all the people who know the secret. By iterating through the meetings in time order and building graphs for each time slot, we ensure that the secret spreads only through valid connections. The use of BFS guarantees that we correctly identify all connected components of people in each time frame. This implementation is efficient and leverages the structure of meetings and the properties of graphs to achieve the desired outcome. The solution concludes by converting the NoSecret set to a list and returning it, which satisfies the problem's requirements. In this example, we are given 4 people and a series of meetings with specific times. The goal is to identify all the people who end up knowing the secret. First, we group the meetings by their time, which helps us process them in chronological order. This results in a dictionary where the keys represent the time and the values are the meetings that occur at that time. For instance, at time 1, we have 2 meetings, one between persons 0 and 2, and another between persons 1 and 3. At time 3, there's a single meeting between persons 2 and 3. Next, we initialize the NoSecret set, which keeps track of the people who currently know the secret. Initially, person 0 knows the secret, and since the first person is 1, they are also added to the set. So, at this stage, the NoSecret set contains persons 0 and 1. Now, we process the meetings in chronological order. At time 1, we consider the meetings between persons 0 and 2, and persons 1 and 3. A graph is built where edges represent these meetings. This connects persons 0 to 2 and 1 to 3. The people involved in these meetings are 0, 1, 2, and 3. We then perform a breadth-first search, BFS, starting with the people who already know the secret, which are persons 0 and 1. Person 0 shares the secret with person 2, and person 1 shares it with person 3. This means that by the end of this time step, all 4 people 0, 1, 2, and 3 know the secret. Moving to time 3, the only meeting is between persons 2 and 3. Since both already know the secret, no changes occur. Finally, the NoSecret set remains as 0, 1, 2, 3, and the output is all 4 people. In this example, we have 6 people and 3 meetings taking place at different times. Once again, the goal is to find all the people who know the secret. The meetings are grouped by time, resulting in 1 meeting at each time step. At time 1, persons 0 and 2 meet, at time 2, persons 1 and 3 meet, and at time 3, persons 4 and 5 meet. Initially, the NoSecret set contains persons 0 and 2 because person 0 knows the secret, and first person is 2. At time 1, the meeting between persons 0 and 2 is processed. A graph is created, connecting persons 0 and 2. Since both of these people already know the secret, there are no updates to the NoSecret set. It remains as 0, 2. At time 2, the meeting between persons 1 and 3 is processed. A graph is built connecting these two people, and the set of people involved includes only persons 1 and 3. However, no one in this group currently knows the secret, so the BFS does not start, and there are no updates to the knows_secret set. Similarly, at time 3, the meeting between persons 4 and 5 is processed. A graph is created connecting these two people, but again, neither of them knows the secret, so the knows_secret set remains unchanged. By the end of all the meetings, the output is 0, 2, indicating that only persons 0 and 2 know the secret. Now let's look at an example where the meetings form a large connected component. Here, there are 5 people, and all the meetings take place at the same time, which is time 1. The meetings connect persons 0 and 1, 1 and 2, 2 and 3, and 3 and 4. This creates a chain-like structure where every person is connected to their immediate neighbors. Initially, the knows_secret set includes persons 0 and 4 because person 0 knows the secret, and first person is 4. With this setup, we have a connected component spanning all the people, and we need to determine who ends up knowing the secret. At time 1, all the meetings are processed together. A graph is built where each person is connected to their neighbors, forming a chain. Person 0 is connected to 1, person 1 is connected to 0 and 2, and so on, until person 4. The people involved include everyone from person 0 to person 4. The BFS starts with persons 0 and 4 since they initially know the secret. From person 0, the secret is passed to person 1, and from person 4, it is passed to person 3. Then, person 1 shares the secret with person 2, and person 3 also tries to share it with person 2, but person 2 already knows the secret by that point. At the end of this process, everyone in the chain, persons 0, 1, 2, 3, and 4, ends up knowing the secret. The final knows_secret set is 0, 1, 2, 3, 4, and the output includes all 5 people. To analyze the time complexity of the algorithm, we start by considering the different steps involved. First, we group the input meetings, which has a size of m, by their time. This step involves iterating through the meetings and takes m time. Next, we process these grouped meetings in chronological order. Since the times are grouped, sorting these unique times requires k*log k, where k is the number of unique times. For each unique time, we perform 2 main operations. The first is building a graph, where we iterate over all the meetings happening at that time. If p people are involved in these meetings, constructing the adjacency list for the graph takes p. The second operation is performing breadth-first search, or BFS, starting with people who know the secret. In the graph, if there are p nodes and e edges, BFS takes e plus p. Since the number of edges, e, is proportional to the number of meetings, this step also simplifies to p. When we consider all unique times, the total cost of building graphs and performing BFS across these meetings is proportional to the total number of meetings, which is m. Now that we have broken down the steps, the dominant operations in this algorithm are sorting the unique times and performing BFS across the meetings. Combining these, the total time complexity is k*log k plus m. In the worst case, if all m meetings happen at unique times, meaning k equals m, the time complexity becomes m*log m. Next, for the space complexity, we analyze the storage requirements. The meetings _by_ time dictionary stores all m meetings grouped by their times, requiring m space. Then, for graph construction at each unique time, the adjacency list representation of the graph requires p plus e space, where p is the number of nodes and e is the number of edges. Since e is proportional to p, the graph storage simplifies to p. Across all unique times, this graph space is proportional to the number of meetings, so it totals to m space. In addition to the graph storage, there are auxiliary data structures needed during computation. The BFS process uses a queue and a visited set. The queue size is bounded by the number of people in the graph, which is p. Across all unique times, this requires m space. Additionally, the knows_secret set keeps track of the people who know the secret. In the worst case, all n people could learn the secret, requiring n space. When we combine all these storage requirements, the total space complexity is m plus n. Comparing this to a brute force approach, which would involve simulating each meeting and propagating the secret through all pairs of people, the naive solution would result in a time complexity of O n squared asterisk m, which is computationally expensive. In contrast, the optimized approach leverages sorting and graph traversal to minimize redundant operations, achieving a much more efficient time complexity of O m asterisk log m in the worst case. Now let's examine the best, average, and worst case scenarios for this algorithm. In the best case, if all meetings occur at the same time, the graph construction happens just once, resulting in a time complexity of O m. In the average case, meetings are typically distributed across a few unique times. Here, the complexity is O k asterisk log k plus m, where k is relatively small compared to m. In the worst case, where every meeting occurs at a unique time, the sorting cost dominates, leading to O m asterisk log m. To summarize, the time complexity in the worst case is O m asterisk log m, and the space complexity is O m plus n. This algorithm is highly efficient for large inputs, as it strategically uses graph traversal and time-based grouping to significantly outperform the brute force approach. In this problem, there are a few common mistakes that can lead to incorrect or inefficient solutions. First, it's important to note whether the problem specifies bidirectional or one-way communication. If meetings are directed, meaning person A tells person B but not the other way around, ignoring this detail can result in completely wrong answers. Next, the order of processing meetings is critical if the problem specifies a chronological sequence. Failing to sort meetings by time can lead to propagation happening out of order, which disrupts the logic. Another issue is handling duplicate meetings. If two people meet multiple times, some solutions might process each meeting unnecessarily, slowing down the algorithm. Using as set or skipping redundant meetings can help optimize performance. Then, there's the need to account for edge cases, situations like no meetings occurring, everyone already knowing the secret, or isolated individuals who never meet anyone. These edge cases can break your solution if not handled properly. Finally, be cautious with your propagation logic. Accidentally marking someone as knowing the secret too early, before they've actually received it, can cascade into more errors. Always ensure the logic for spreading the secret is strictly accurate. Now, let's consider some insights specifically for interviews. Problems like these often boil down to how you represent the data. Graph representation is key. Each person can be thought of as a node, and interactions like meetings form edges. Mastering graph traversal techniques such as breadth-first search, BFS, and depth-first search, DFS, will allow you to solve these efficiently. Another consideration is whether to use brute force simulation or mathematical shortcuts. Simulation is straightforward and intuitive, but it can become inefficient for larger inputs. For example, Union Find is a powerful tool for efficiently managing connected components, which can often replace brute force. Be prepared to articulate the trade-offs between these approaches in an interview. Lastly, take problem constraints into account. For instance, if the input specifies up to 10,000 people or guarantees meetings are sorted by time, these details can guide your approach. Sorting meetings has a time complexity of O n log n, which might be necessary, while simulating every meeting could lead to O n squared complexity. Always align your chosen method with the constraints given. Let's look at some related problems and alternative approaches that can help solidify your understanding. A few similar problems include LeetCode 277, which involves finding a celebrity, a person who is known by everyone but knows no one else. Then there's LeetCode 547, which explores the concept of connected components in a graph, similar to spreading information. Another is LeetCode 997, where you identify the town judge, again dealing with directed influence. Finally, LeetCode 841, Keys in Rooms, involves simulating access or information spread through a network. As for alternative approaches, brute force simulation is a good starting point to understand the problem and verify initial logic. However, it's inefficient for larger inputs, typically running at O n squared time complexity. A more advanced alternative is the union find or disjoint set union approach. This is highly efficient for scenarios where the problem boils down to grouping people into connected components. By using path compression, you can achieve a time complexity of O n log n, making it suitable for larger datasets. Additionally, BFS and DFS are excellent techniques for graph-based problems, especially when you need to track propagation in real time. Their time complexity is O v plus e, where V represents the number of people and E the number of connections or meetings. These methods are particularly useful when the network has dynamic or complex propagation paths. Sorting meetings by time is another critical step when the order of events matters. Once sorted, this can be combined with other methods like BFS, DFS, or union find to process the meetings in the correct sequence. The sorting itself has a time complexity of O(n log n), and any additional processing will depend on the specifics of your approach. By carefully combining these tools and techniques, you can tackle a wide range of variations within this problem space efficiently and effectively. Great job following through. To summarize, we tackled a fascinating problem of tracking information spread, starting with a brute force approach. Remember, optimization and complexity analysis are crucial for scalable solutions. Thanks for watching, and we'll see you next time with more exciting challenges. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!